Hello, this is Professor Slaughter, and in this video we're going to review how data is described in statistics. We're going to talk about central tendency, means, medians, and modes. I'm going to go over variance and standard deviation. I'll introduce you to Chebyshev's theorem and the empirical rule. Now you'll have to decide on whether or not you want to listen to the lecture first or read the chapter first. But regardless of your decision, you should do both. I will go over concepts in this lecture and review a few examples, but some of the details you should know will only be presented in the textbook. And when we're talking about data that is described, we're dealing with quantitative data. Quantitative data means that the data is presented in numbers. We are looking at location and dispersion of the data. Now, measures of location include means and averages, and measures of dispersion describe how the data is spread out. Now, since most of us are already familiar with averages, let's start with means. The formula for mean in your textbook is right here for your population mean. And the mu, this character here, stands for population mean, and the n stands for the number of values in the observation. Now the x right here represents a value, and the sigma is basically the summation, all right, the sum. So the sum, sigma x, would mean add all the x's together. So most of us deal with averages on a daily basis, but let's apply the formula so that we know what it means. I'll show you an example in Excel. And although software is not required in this course, if you have a talent for Excel, you might want to use it. So let me stop here for a second and bring something to your attention. In all of my quantitative courses, I recommend that you decide on two methods that you're going to use to solve problems. In this course, you can use a calculator, Excel, or work with the formulas. For the most part, I work with the formulas and the calculator, but I will also switch back and forth with Excel when things get hectic. I sometimes have to rely on the calculators, though. I will warn you that you do not want to become dependent on calculators. On test, you will be required to show your work in order to get credit for the answer. So keep this in mind when you are practicing. So going back to this formula, going back to the formulas, we also have a formula for calculating a sample mean. And a sample mean, when you look at the formula, I want you to see if we can compare these together. Here we have mu and x bar have similar meanings. Here the mu is what is considered the average of the population, and in this case x bar means the average of a sample. Okay, we have the sum of all x, and in this formula we have the sum of all x. And for the population, we have a capital N, because that is the number of values in the population. And here we have N as the number of values in the sample. So when we're working with means, understand that whether we are calculating the mean for a sample or a population, mechanically it's the same thing, even if the formulas look a little different. Now keep in mind that if it is possible for you to calculate a mean, then you're working with interval or ratio level data. And if you are going to calculate a mean, then you make sure that you include all the numbers that you're given. Don't leave anything out. There is a fourth thing to consider, which would not be understood at this point, but it basically means that if we add the deviations of each value from the mean, then they will all total 0. But since we haven't gotten into deviations, that won't make a lot of sense right now. Another type of mean that we will work with in statistics and finance and math is weighted mean, but I want to show you this Excel formula first and how that works. Okay, so if you look at your example in your book on page 61, specifically, let me make this a little bigger for the video if I can. Okay, we're looking at the example on page 61. What I've done is I have retyped into Excel all of these values. Okay, and you'll see that they're right here. And so when we calculate a mean, we do the same thing that we do when we're averaging something. When we average something, we add it all together and we divide it by the number of things that we're looking at. Same thing in statistics. When we look at the total, we're going to add all of our data together, all of our observations together. I'm going to go ahead and use Excel to add all of this up. So we add it up, and when we add all these numbers together, we get 192. So let's go back and look at if we're correct so far, and you'll see in the solution it says the total distance is 192 miles. And then we want to know how many of these observations do we have, right? So now we're going to just count how many observations we have. And we have 42 observations. Are we correct? Yes, we add the distances between each of the 42 exits. So if we add all these numbers together, the number of numbers that we have is 42, and they total 192. And then when we take 192 and we divide it by 42, we get 4.571429. And when we round that off, whoops, that's not what I wanted to do. I wanted to remove decimal points. Make this column a little bit smaller again. Oh, too small. Okay. We get 4.57 miles. Okay. And when we look back at our book, it says that the mean is 4.57. So we calculated this correctly. So again, what we're doing is we're taking our observations, we're adding them all together, and we get 192. And then when we count the number of observations that we have 42. And when we divide 192 by 42, we get 4.57. Okay, so that gets us through the mean part. Now, like I was saying, another type of mean that we will work with in statistics, finance, and math is a weighted mean. And you may already have worked with this in calculating your final grade in some of your courses. There's an extra step when calculating the weighted mean. So what I did is I took the example from your textbook. Let's move over here. Weighted mean. We're going to go to page 65, and we're working this example that's in your textbook. Now you'll see the Carter Construction Company pays its hourly employees $16.50, $19, or $25 an hour. There are 26 employees, 14 of which are paid $16.50, 10 at the rate of 19, and 2 at the rate of 25. And what is the mean hourly rate paid to the 26 employees? So we're looking for the average hourly rate paid to the 26 employees. So I went ahead and I put this information in an Excel spreadsheet. So we have 16, 19, and 25 as the hourly rate. And there are 14 employees that get paid $16.50. There are 10 that get paid $19 and 2 that get paid $25. And when I add that up, I account for all 26 employees. Again, when we're dealing with averages, we have to make sure that we include all the data. So I add these up, make sure I've got everybody. Then what I do is I take 14 and I divide it by 26 to give me the weight of that hourly rate, which in this case is 0.5384. Now these numbers are pretty small with so many decimal points, but typically I'll leave my decimal points way out there until my final answer when I start rounding things off. But you can round this up probably to 4 or 6 digits and be just fine. So when you take 14 and divide it by 26, you get a weight of 0.5384, which is 53.84%. 10 divided by 26 is 0.3846. And 2 divided by 26 is 0.0769. Then we take the weight times the hourly rate. So the weight is here and the hourly rate is here. So when we multiply these two numbers together, we get $8.88. 19 times the weight is $7.31. And 25 times 0.0769 is $1.92. And when we add these up, we get the weighted hourly rate. Now, when the company estimates its hourly labor rate, it uses this weighted average of $18.12. And you'll see that no employee makes $18.12. But each wage bracket contributes to the weighted average hourly rate. Since 53.84% of the employees make $16.50 an hour, the weighted average for that class is, or that observation, that hourly rate is $8.88. The next group is 38.46% of the employees, and they make $19 an hour, which contributed $7.31 to the weighted average hourly rate, and so on. You can see that it would be much easier for an executive to estimate how much the labor costs are in his facility per hour by using a weighted hourly rate. And again, it is not exact by employee, but it is a more accurate estimation of the cost company-wide. So now we're going to look at median. The median is the physical location in a group of numbers, and it's basically a midpoint of all the values presented. So when we look at median in the textbook, we're looking at the example on page 67. Okay, it says Facebook is a popular social networking website. Users can add friends and send them messages and update their personal profiles to notify friends about themselves and their activities. A sample of 10 adults revealed they spend the following number of hours last month using Facebook. So in calculating the median, there's one thing that you have to keep in mind, because you're looking for the midpoint of the numbers. Okay, so when we transfer those numbers into Excel and we type them right here on this first row, okay, 357, 591, 3917, 10. Okay, so when we're calculating the median or the midpoint, the first thing that we have to do is put the numbers in order first. So in the first row, in row 1, the numbers are exactly how they were given in the example. In the second row, I have put them in order from lowest to highest. Now, since there are 10 values given, I count in from each direction 5 values, because the midpoint is going to be the midpoint of the data divided by 2. It's going to be at half. So we have 10 data elements. So when I divide that by 2, that's 5. So I count in 5 from each direction. So here I count in 5 numbers, 1, 2, 3, 4, 5, which gives me that 5 which I highlighted. And then from this side, I count in 5, 1, 2, 3, 4, 5, which gives me a different midpoint, 7. So what you end up doing is adding these two together, which is going to give you 12, and then you divide them by 2. Now, if you had an odd number of data elements, you would just have one midpoint, because when you count it in from both sides, you would get the same midpoint. But in this case, because we have an even number of data elements, we end up with those two numbers, and we have to average those. So we add them together and divide them by 2 to get the median of 6. Okay, so all of the things that we have looked at thus far are measures of location in the data. Now I want to look at standard deviation and variance. Now your book is going to go over this in greater detail, so you need to read the book. But for the purposes of getting through this quickly, I want to give you a way to calculate variance and standard deviation that will be easy for you to remember. And you should take time to study and retain this, because you will see it again in your science classes, in other statistics classes, and in your finance classes as well. So let's look at variance and standard deviation. Now in this example, we will start with the initial column that is basically optional. Let me take you to your textbook on what we're looking at for standard deviation. Okay, give me just a second. I'm looking for the particular example that we're going to be encountering in the video. Okay, so if you look on your textbook page 83, there's an example which is talking about the hourly wages that are paid to part-time employees at Home Depot at $12, $20, $16, $18, and $19. And it asks us to calculate the sample variance. Now I'm going to take it a step further and go ahead and show you how to calculate the standard deviation, but this is where I'm getting the data. So if you want to turn to page 83 in your textbook so you can see how I set up the Excel spreadsheet, then that will help. Okay, so hopping over to Excel. Again, I set it up. This is optional. This just tells me that I have 5 different hourly rates from the problem: $12, $20, $16, $18, and $19. Now this column, this optional column here, you can use it or not use it. For me, it helps me track the number of observations I have. But in this case, we are actually evaluating the hourly rates of part-time employees. So the first thing that we're going to do when we're calculating variance and standard deviation is we are going to add all the hourly rates together, which is going to give us 85. So we're adding all these numbers together, which is going to give us 85. And this is the value. This 85 is what we call the sum of all x. Okay, well, here's our x. We have 5 values for x, and so this is the sum of all x because we added them together. Then we divide that number by the number of observations, which in this example is 5. Okay? When we divide 85 by 5, that gives us the answer to the formula, the sum of all x divided by n, which in this case is 17. And once we have the answer of 17, we can calculate the second part of the formula, which is x minus x bar. Now in this example, we subtract 17 from 12. That gives us -5. We subtract 17 from 20, and that gives us a +3. We complete the chart in the same way for all these observations. Now it's hard to work with negative numbers when we are trying to calculate variance and standard deviation. So to get rid of the negative numbers, we square them. And that means that the -5 becomes 25, because when we square a number, we just basically multiply it by itself. 5 times 5, which will give us 25. 3 times 3 gives us 9. 1 times 1 gives us 1. And so on. So the next step is to add together the square of the differences, and that's exactly what this is called. The differences are the squared differences, and when we add all of these together, we get 40. Now here is where we have to make the adjustment for a sample, because in this example, the book tells us that we are working with a sample. We have to adjust our n. And our n is 5. That's the number of observations that we have. To adjust the n for working with a sample, we calculate n minus 1, which in this example gives us 4. So when we divide 40 by 4, we get a $10 variance, which is represented by S2. The sample variance is always represented by S2. S squared. And we take And when we calculate standard deviation, all we're doing is we're taking the square root of the variance, which gives us the standard deviation. So the square root of 10 is $3.16. Now, it is in this manner that we will calculate variances and standard deviations for the remainder of the semester. So it's important that you learn this process. Now, reading your text about Chebyshev's theorem and the empirical rule, because it kind of explains how the data is shaped. In the empirical rule, substantially all of the data points will be within 3 standard deviations of the mean, and according to Chebyshev's theorem, it would go out further. So I want you to make sure that you read that. And I think after you've had this video and looked at a video that I'm going to be adding after this that's just going to explain the normal distribution curve, I think that you'll be fine on understanding those when you encounter them in your textbook. So hold on just a second. You're going to transition over to an earlier video that's going to explain what the distribution curve is, as well as what a variance or what the standard deviation actually is when you're looking at the normal distribution curve. Okay, so I'm going to wrap up the video that you just saw with a basic explanation of the distribution curves, and we're going to look at Chebyshev's theorem as well as the empirical rule. You know, in the textbook, it really doesn't go in, it doesn't seem to explain it very well in the differences, so it doesn't highlight the differences to the extent that I think you'll pick them up. So first of all, let's talk about the empirical rule. Now, this is typically what a normal distribution curve will look like, and this is a symmetrical symmetrical distribution curve, and basically what that means is that both sides of the curve look exactly alike. So when I say both sides, what am I talking about? Well, usually in a normal distribution curve, somewhere around here is where your mean's going to be. That's not exactly perfect. It usually is perfectly symmetrical, and my lousy handwriting, I didn't get it quite right, but this is basically what a distribution curve looks like. So we're going to highlight the mean line in yellow so we don't lose track of it. And so in this normal distribution curve, our data, and we'll just show these as points under the distribution curve, our data appears all over the place, and even maybe a few outside the normal distribution curve as well. Okay, so what is a standard deviation? Well, a standard deviation is a distance from the mean. Okay, it's a measure of dispersion, but it's also distance from the mean. So if we draw these other lines and we count each one of these as a standard deviation. All right, so I want to this is 1, 2, and 3. You'll notice that I put one standard deviation away from the mean on both the left and the right because it's still the same distance. Two standard deviations left and right of this curve of the mean, and 3 standard deviations left and right of the mean. Okay, so in our example in the earlier video, we came to the conclusion, I believe if I'm remembering correctly, that our mean was $3.16. So I'll just go ahead and put that here to remind us that this mean actually has a value. So let's say that the standard deviation was 50 cents. Okay? So when we look at what a standard deviation is, basically we're saying each standard deviation is worth 50 cents. So that means that the first standard deviation is worth 50 cents, the second standard deviation is worth, every single standard deviation, even if it went beyond 3, they're each worth 50 cents. All right. So then here, when we're looking at this example, and we have a mean of $3.16, and we add 50 cents to it, we end up with $3.66. And then when we add another 50 cents, $4.16. And when we add another 50 cents, we end up with $4.66. And then when we add another 50 cents, we end up with $5.16. And it works the same way going to the left. Remember, when we're working with normal distribution, it doesn't necessarily mean when we go left on this axis that we're going into negative numbers. So when we take $3.16 and we lower that amount by 1 standard deviation, we're at $2.66. And then we do it again, and we are at $2.16. And for the third standard deviation, that's at $1.66. And if we go ahead and take it out to 4 standard deviations, we end up with $1.16. So when we're looking at the empirical rule, the empirical rule basically applies to normal distribution curves. It's sometimes called the normal rule. And this is basically what it means. With the normal distribution curve, the rule is that within one standard deviation of the mean, left or right, 68% of your observations or 68% of your data is going to be within one standard deviation of the mean. If we take it out to 2 standard deviations, then we are looking at 95% of your data. Now this is assuming that your data is appearing in a symmetrical bell-shaped frequency distribution like this. And then if we go to 3 standard deviations, whoops, went too far there. So let's get rid of this line before we cause some confusion here. Get this cleaned up a little bit. Okay, so within 3 standard deviations, 99.7% of your data will fall between these 3. Okay, so we're looking at between 1 standard deviation, 2 standard deviation, and 3. And for the most part, this would mean that 99.7% of your data would fall within this part of the curve, and that's substantially all of your data. Now when we look at Chebyshev, I always have a hard time pronouncing his name, Chebyshev's theorem, it's a little bit different because Chebyshev is doing the same type of thing, but he's doing it on a distribution curve regardless of the shape of that curve. So if it skews to the left or it skews to the right, that's when we look to Chebyshev's theorem. Okay, so I'll use pink on this to show how he's a little different. He says that 75% of the data, he starts with 2. Okay, so he says that 75% of the data must fall within 2 standard deviations, and then he jumps it up to 3 standard deviations. So if we go out to 3 standard deviations, he says that 88.9% of that data is 88.9% of your observations will be within 3 standard deviations, and he goes all the way out to 5 standard deviations, which is outside the scope of this drawing. Okay, and he says that 96% of the data will lie within 5 standard deviations. So with Chebyshev, we're looking at distribution curves. His rule applies to curves that might look like this, with the mean that might be off-centered, okay, as opposed to something that's symmetrical. So if it's symmetrical, we use the empirical rule, and if it is shaped a little differently, we would probably do better to rely on Chebyshev's theorem. So I hope this helps you understand, with giving you the background information in the original video. I hope that this helps you understand exactly what a standard deviation is, and that it does have a physical location in the distribution curve.